Okay, so let's try this test. 4.3, 4.5 summative test. The first section is on basic concepts. So things like period, frequency, wavelength, or wave speed equation. So let's start with the first one, which should have been really straightforward. 40 waves pass a given point in 12 seconds. So 40 waves in 12 seconds. Calculate the frequency. Well, the definition of frequency is how many waves per second. So if you get 40 waves in 12 seconds, how many waves do you get in 1 second? So that would be 40 divided by 12, which gives you 3.3 hertz. Okay, those are the correct units, and the number of significant figures should be 2. The period of the waves would then be using the following relationship. 1 over period equals frequency. So 1 over 3.3 would give you a period of 0.3 seconds. So that would be your answer for period, and your frequency would be 3.33 hertz. And that would give you 2 marks. Question 2 is also examining some really basic concepts. So the first one would be find the period, the amplitude, the frequency for the following wave. Now the period is the time for one wave. First check that on the x-axis you have time. Yes. So the period would be from the point of origin here to when the wave gets to that point again, which would be here. So the period would definitely be 8 seconds. Very important to include units there. The amplitude, that's asking you to identify that you know what the amplitude is. It's this height here, which you can see is 1 meter. So the amplitude is 1 meter. And the frequency then would just be a simple calculation. Frequency equals 1 over 8, which is 0.1, or which is equal to 0.125 hertz. Please remember units. Still with some basic concepts, we have question number 3. A wave period of 5 milliseconds travels through a medium. The graph shows the variation with distance d of the displacement x of points in the medium. So here we have a displacement displacement graph as opposed to period. So now they want you to work out the average speed. Now the average speed, wave speed formula, is equal to frequency times wavelength, and this c is sometimes written as a v. Okay, which is fine. So both are good. So let's see if we can find the wavelength now, because it's a distance a displacement distance graph, then you can read the wavelength straight here. It will be the distance here, if I mark it. Starting here, it would be the distance for the wave to get to exactly the same position, which is at maximum displacement. So the distance, which is equivalent to the wavelength, is 2 meters. And you have to check the units here. It's really important. So you've got your distance, and now let's see if we can find the frequency. Well, we know the frequency is 1 over the period, and the period is 5 milliseconds. So 1 over the period would be 1 over 5 times 10 to the minus 3. So the frequency would be equal to 200, right? So frequency is equal to 200, because that's 1 over 0.005. So 2 times 200 equals 400. So the answer is definitely D. Some of you wrote B because you didn't realize it was 5 times 10 to the minus 3 milliseconds. Always important to check units. Okay, next one. Progressive waves, S and T, have the same frequency and are in the same medium. S has an amplitude of 2 and T has an amplitude of 4. What is the ratio of the intensity? Now you should remember that intensity is proportional to amplitude squared. So whatever it is that you do to the amplitude, you then have to square it in order to give you the intensity change. So if amplitude of S is 2 and T has an amplitude of 4, so basically the amplitude of T is twice that of S. So what I'm going to do is I'm going to take S and I'm going to double it. So what would happen if I was to double this amplitude? Well, the intensity then would be 2 squared, which would give me an intensity which is 4 times greater. So the intensity of T is 4 times bigger than S. So the ratio of intensity of T to intensity of S is 4. The answer is D. Similarly, question 5. The intensity of radiation from a star at a surface of one of the planets is I. So let me make this a bit bigger so I can sketch it out. Now, you have a distance D and an intensity I. Now, what is the intensity at the surface of another planet, which is at D over 4? So now we're going to put the planet here. And that distance is D over 4. Okay, now the relationship is intensity is proportional to 1 over D squared. So what's happened? In planet 1, we would say that the intensity is I. Okay, but planet 2, what we've done is we've made D 4 times smaller. I've drawn it here a little bit neater. So if I make D 4 times smaller, basically, what I've done then to the intensity is I've made the intensity 4 squared, right, because it's a D squared relationship, not a D squared. But because it's a divided by, it's a denominator that actually affects it up here, and it makes it 4 squared. The intensity is 4 squared times bigger. It's actually 16 times more intense. And if you think about it, would the light be brighter as you were closer? Yes, it would. So the number would be increasing. And it's just basically understanding that it's a D squared relationship. So the answer would be C. Question 6. We have light from a source which has an intensity x at a distance of 10 meters. Calculate the intensity of the light at a distance of 100 meters. So this is actually a slightly easier question, I think, than question number 5. So if we sketch it out, okay, so if we have a relationship which is I, intensity is inversely proportional to distance squared, and here we have a distance 10, and the next part of the question is at a distance 100. How many times bigger is the second distance? It's 10 times bigger, because 100 over 10 is 10. So if we now need to find what happens to the intensity if we make the distance 10 times bigger, well, because it's the square of both terms, 10 squared would give you 100, which means that the consequence is that the intensity would be 10 squared times smaller, which is 100 times smaller than it was before. And one of the easiest ways of thinking about this is, okay, if it's further away, then the distance is going to be much less. Okay, so that's a good starting point for solving these questions. And if the distance is much less, then you just do 10 squared gives you 100. Okay, so the intensity goes down by 100. Question 7. Now this is a really straightforward question about polarization. And what you have is unpolarized light, which is incident on the first polarizer. Now what that first polarizer does is it removes 50% of the intensity straight off. Now what that means is that the light here is polarized too, and then the second polarizer will produce an intensity which is much lower. Okay, so if we look at our equation of the equation for polarization, which is the intensity that you get out, this new intensity, IF, is equal to the initial intensity, which would be this initial intensity, arriving at the second polarizer. So it's I naught, I haven't got much room, let me just do that, cosine squared of the angle, right? Now the question states that IF, final intensity, is equal to 80, right? So therefore, if we put IF in our equation and we use 60 degrees here, okay, substitute your values in, you should be able to work out I naught as equal to, should get value of 320 watts per meter squared. Okay, so -2 should be a minus. Okay, so that was simple enough. And then we need to go to part 2, which is asking you, well, what is the intensity of light reaching the first polarizer? And if the first polarizer reduces the intensity by 50%, if we have 320 here, then we must have had 640 before. So the answer would be watts per meters to the -2. Okay, so question number 8. Unpolarized light of intensity I naught is incident on a polarizer with a vertical transmission axis. Okay, so it's along this line. The transmitted light is then incident on a sheet of material X. The transmission after going through X is I naught over 2. So basically what's happened is absolutely nothing, right? You had I naught over 2 here because of the first polarizer, and then exactly the same later. Now the only way that this could happen is if you have a polarizer that's exactly the same as that one. So it has a vertical transmission axis. And then the other option is absolutely nothing, that you have a non-polarizing glass, maybe something that's purely transparent. So the answer is A. Now question 9 is by far the trickiest question. So what have we got here? A distance between X and P and Y and P, which results in waves destructively interfering. So that means that this distance, XP, is in antiphase with this distance YP. Now that kind of doesn't make sense because I've used distance and phase together. It's basically saying that when YP carries the extra distance of 0.60 meters, it's obviously 0.60 meters longer than XP, and that is equivalent to half a wavelength. Now it's tempting to think if that's half a wavelength, then it could be 1 meter 20. It can only be 1 meter 20, but it's not quite that simple. That could be half a wavelength, or it could be 1.5 wavelengths, or it could be 2.5 wavelengths. So what you have to kind of do is work your way through the answers that are possible. Basically, by deduction, if the wavelength was equivalent to 0.6, then an entire wavelength would be 1.20, and that's not an option. So we need to go for the next one. If the wavelength was equal to 1.5 wavelengths, then it would look like this. Okay, we could build an equation that would look like this. So that gives us 0.6 equals 3/2 wavelength, which would give you a value of wavelength as equal to 0.4. So luckily you didn't have to go too far, you didn't have to do all of them to finally get an answer. So the answer is C. Okay, so question 10, we have a wave diagram that's showing you refraction. Now the first thing that you need to remember is that if the media or the material is thicker, if the light is traveling, or the wave, sorry, is traveling into a material which is thicker, denser, then it would bend towards the normal. Let me draw that properly. Okay, I've tried it a million ways to come up with a straight line with this program, and I can't do it. So this will have to do. That squiggly red line is supposed to show that it bends towards the normal. Okay, so when it goes in, and then it bends towards the normal. So basically, you should have either this one or this one. It can't be these two because they're bending away from the normal. Now, the next question is, what happens to the wavelength when it goes into a denser material? Well, as you should remember, the wave slows down, and because we have wave speed formula, if the wavelength has to reflect the speed, if the speed slows down, the wavelength has to get smaller because the frequency stays the same. So the answer is B. Where did that ruler come from? Question 11. So this one is about just remembering or using, not even remembering. All you had to do was look up Snell's law, which is in the data booklet. And yet some of you still didn't get this right. So you should remember that sine vacuum. So I'm going to use 1 and 2, use that notation. Sine 1, angle 1, over sine angle 2 equals the velocity in 1 over the velocity in 2 equals the refractive index of 2 and refractive index of 1. So I was hoping you'd remember that the refractive index part of the equation just splits. Spits? No, spits. It doesn't spit. It doesn't split. It flips, right? So it flips round. But this should be in the data booklet. In fact, quite a few of you got this wrong, so I'm going to just check it's in the data booklet. It is in the data booklet. It's just written differently. So in the data booklet, it's written like this. Okay, so it's just the other way around. But anyway, from this, you should be able to tell that the refractive index of glass, well, let's have a look. Let's use the equation. Okay, I'm going to simplify it a bit because in the end, we don't actually need any of that, any of this bit. Why isn't this working? We're just going to look at this. Sine of the angle, right, which will give you the refractive index of glass. Well, because you want the refractive index of glass, you get 1 over n2. So 1 over n2. Why is it 1 over n2? Because a vacuum, n1 is equal to 1, right? So that equals v2, which is v over v1, which is the speed of light, because that's the speed of light in a vacuum, right? So now, if we flip it around, because we don't want 1 over n2, we want n2. n2 is equal to c over v, which is A. And well done, those of you who got that right. And those of you who got it wrong, I'm not quite sure what to do with you. Question 12. We're going to use exactly the same equation, but this time to actually calculate some values. So let's give it a go. So again, we've got light coming from air into glass, and you've got to find the angle 1. So if we go back to our equation, this is Snell's law, and so this would give you 1, the refractive index of 1, which is in air, is 1 over 1.5, which is the refractive index of glass, equals sine 30 over sine of our unknown angle. If you solve for that angle, you should get an angle of 49 degrees to two significant figures. You then use exactly the same equation, but this time to find the velocity in glass. So 1 over 1.5 equals the velocity in glass over the speed of light in air, which is the same, we assume. Okay, it's 3 times 10 to the 8 meters per second. So that would give you a velocity in glass of 2 times 10 to the 8 meters per second. Okay, so it was quite a straightforward question. Part 3 was about the critical angle for glass. Now the critical angle, as you should remember, is the angle at which light hits a boundary between two surfaces, right, coming in from the denser material, and a critical angle is the point at which this refracted angle, this would be the refracted angle, is actually equal to 90 degrees. Whoops. Okay, so as a quick little review, if we use Snell's law, we have sine I over sine R equals N2 over N1. Now N1, if we assume that this is air, so this formula only works in this particular situation, then N2 would be equal to 1, and sine of the incident angle would be the critical angle, and then sine of the refracted would be equal to sine of 90 degrees. Okay, so the equation then becomes sine of the critical angle equals 1 over n of the first material. Okay, so basically you can find the critical angle by doing or just working out the inverse of the refractive index of the denser material. So let's try that. Okay, so using that equation, sine of the critical angle would be equal to 1 over 1.5, and then if you solve for that angle, you should get 42 degrees. Now what happens when the incident angle is greater? Well, you get reflection. Okay, and that's the whole point of the critical angle. Above the critical angle, you get reflection, and less than the critical angle, you get refraction. And be 0.2. What just happened? Oh good, I've got my pen back now. I don't know what was going on before, but I changed one of the settings, so it should be easier to read now. Now, what do we mean by interference of waves from two sources? Interference, the definition should include the word superposition, which most of you did mention. So it's to do with the superposition of waves to affect the amplitude in some way, be it either constructive or destructive. Now coherence or coherent sources refers to waves that have the same wavelength and frequency, though these count as the same one, and the same phase difference. Okay, so most of you got one of these but then forgot the other. So you'd need to mention 2 to get full credit. Now we have an interference question, and more importantly, a double slits question. So we have figure 6.1 shows 2 microwave transmitters. Okay, so these are acting the same way that 2 young slits would act because they're coherent sources. And they are 5 meters from a receptor or a detector that's moved along here. So what you will note notice if you had a receptor is areas of maxima and minima along P and Q. Now eventually the question is going to ask you to calculate something, so I'm going to do that first because I can't come back to this page later. Now in part B2 it will ask you to calculate the distance between the two intense points, so basically asking you to work out the distance from here to here. Yep. And so we can work that out now using just the equation for Young's double slits. Now the equation pretty much just looks like this, where x is the distance that we're looking for. Yes, I do have a rather hyperactive cat in the vicinity. I'll try and ignore it for a while. Big D is this distance here. The wavelength is 30 millimeters, and the little distance is the distance between the sources. Okay, so it's just plugging in the formulas to that equation, and I don't think there's any tricks to it. The only thing to bear in mind is that this would be 30 times 10 to the minus 3, and I think that's it. There's no other sneaky bits. They're all in meters. So you plug in those values into the equation and you should get 0.75 meters. And I think most of you got that. I think all of you got that right. In which case you wouldn't be listening to this, because if you've got it right, you should fast forward. Okay, so use the idea of path difference or phase difference to explain how the interference pattern is formed. So basically you've got to say, and I made this out of 2 marks. 3 marks I think is a little, that's basically what an IB question would be worth. But I think here I just wanted to hear some basic understanding, and so I marked it more generously. But if you have 2 sources, and it's the path difference which causes, so path difference would cause constructive interference as long as the path difference was equivalent to a wavelength or some integer value of that wavelength. If the path difference was equal to half a wavelength or some integer value plus, that should be a plus half a wavelength, then you would get destructive interference. So any kind of explanation which sort of mentioned constructive, destructive interference as a consequence of the amount of path difference that you have would have got you that credit. Yes. So anyway, here we've done this bit, and then the next question, which is a really common question, it's actually really straightforward, but most of you just didn't read the question. The question states, in effect, state the effect, if any, on the position and the intensity of the maxima when each of the following changes is made to the experiment. So when you've got your sources giving off your radio waves, and on your sensors PQ, you basically can register these maximum points of intensity. What it's asking you is, what happens to the amplitude, how bright the areas are, and then what happens to the distance between them, which is called x. Right, so we're talking about 2 physical laws. The first one is to do with the equation. Okay, so the distance x will be affected by this equation. We can even rearrange it by putting the d, this capital D over here. The second part of the question is about amplitude. And of course, the amplitude, the brightness of this, my pen's not working, hang on. What I mean by the amplitude is the brightness of this one would be affected by any number of things. So, including, of course, the amplitude of the initial source, right? Okay, so the first one, how does the amplitude of the transmitted waves doubling affect those two things? And what you should have noted is, firstly, amplitude is totally irrelevant to this equation, and so definitely here nothing would happen. So x would stay the same. But if you double the amplitude here, then what happens is, because intensity is proportional to amplitude squared, the intensity here would also increase, but by a factor of 4, which is 2 here, squared equals 4. So x is the same, but amplitude, sorry, not amplitude, intensity is 4 times greater. In any case, if you wrote that the intensity was greater or stronger or brighter, I would have given you the credit. Okay, so if we try, the separation between the transmitters is halved. If I just rewrite this equation again. Okay, what we're in fact doing is, by reducing the distance d by half, then what we're doing is doubling x here. So it's a little mathematical exercise. Okay, so the distance will double, distance x, but if you remember, intensity proportional to amplitude squared, there'll be no change to the intensity. Now, what happens in question 3 when the phase of the transmitter is reversed? Well, what happens is that you get a situation where once you had constructive interference, now you will suddenly get destructive interference. So you're going to get those swapping. Now this gives you an interesting answer, because the distance x in effect does not change, right? But what happens is the relative positions of the bright and dark fringes do all swap. So you could say that x is the same, or you could say that it changes in the sense that what was constructive is now destructive. As long as you explain it competently, you should get the credit. Now, with amplitude and intensity, the intensity doesn't change. However, you could argue that the bright fringe now becomes dark. So you could also argue that you could say the intensity now is 0 in that same point, because there is now destructive. So both are correct. If you say I is the same because it's, nothing's happened to the amplitude of the emission, then you're fine. But if you said that the intensity increases, that's fine as well. Okay, I hope that made sense. Question 14. This is like the more complex situation where you have closed at one end and open at the other. And so what we're going to do is quickly derive the equation. Okay, so what we've got here is wavelength, which is equal to 4L, because this section here, as you can see from this diagram, is a quarter of an entire wavelength. So using L, or in terms of L, the wavelength is equal to 4 times L. Now, the frequency associated with that, which in this case would be the fundamental frequency, is the velocity over 4L. And this comes from the wave speed formula, which I'll put here, V equals frequency times wavelength. So that is F. Okay, this is the next level of complexity to this question. F is equal to V over 4L. So now what happens in the next highest harmonic? Well, let's have a look. Our next highest harmonic is as follows. We have a wavelength which is now equal to 4L over 3. And if you're not sure why, have a look at the entire wave. If we divide the length L into 3 sections, 1, 2, 3, then we end up with a quarter of the wavelength, okay, because each one of these is equivalent to a quarter. And then to make the full wavelength, you would multiply it by 4. Okay, so it's L over 3 times 4. Now, the frequency would be equal to V over 4L over 3, which flips up here. Now we need to express which one of the following is the frequency of the next highest. Well, you need the new frequency in terms of the old frequency. And as you can see, that this one is 3 times bigger than the original fundamental frequency. So the answer is D. Okay, so this question is about a ukulele, and as you know from stringed instruments, you get standing waves which are fixed at both ends. Now, what could the graph below be? Well, what you can see here is that you have a displacement section, so this would be displacement, and then this is like a snapshot. It's a photograph of the wave, really, isn't it? So it's got a position aspect to it. You could even argue that this must be distance, right? Distance, because it's only in the plus. However, that would be more like an IB level question, and I'm just testing you for basic understanding at this stage. But do bear in mind the fact that it's a positive means that the direction's not important. So if you've written distance or displacement, I've given you credit, but it should actually be distance. And now we have a straightforward question about fixed at both ends standing waves. Okay, so we have a particular string on a ukulele has a length L of 35 centimeters. Okay, state the wavelength of the wave. Now the full wavelength as a function of the length L would be 2L. So 35 times 2 would give you 70 centimeters, or more appropriately 0.7 meters. Okay, I'm hoping it's a little bit quieter now. So let me do the last question finally. The string is now oscillating at a frequency of 196. Then to calculate the speed, we just need to multiply frequency times wavelength, which gives us the speed. So 196 times 0.7